Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent depths of space, where a wandering comet named 3I Atlas moves through darkness, and where the solar wind flows like an invisible river that never sleeps. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Far beyond the orbit of Neptune, where sunlight arrives as little more than a bright star against the cosmic dark, something ancient stirs. It is a comet, designated 3I Atlas by those who first noticed its presence through telescopes on Earth. The I stands for interstellar visitor not born within the sun's gravitational embrace, but somewhere else entirely. In the space between stars, it has traveled for millions of years, perhaps longer, crossing distances so vast that human timescales dissolve into irrelevance. Only now, as it falls inward toward the sun, does it begin to wake. The comet's nucleus measures perhaps 2 kilometers across, though exact dimensions remain uncertain. It is not a sphere, but an irregular lump, tumbling slowly through the void. Its surface is darker than coal, blackened by cosmic rays and the slow chemistry of deep space. For eons, this object has been frozen locked in temperatures just a few degrees above absolute zero, where molecular motion nearly ceases, where even helium would solidify given enough pressure. But now, distance decreases. The sun's gravity pulls gently but inevitably. And with each passing day, photons arrive in slightly greater numbers. Somewhere in the comet's structure, embedded within ancient ice, are molecules that predate the solar system itself. Water mixed with carbon monoxide, carbon dioxide, methane, ammonia, simple compounds frozen in ratios that tell stories about the nebula from which stars form. There are also complex organics, the carbon-based molecules that form in interstellar clouds when ultraviolet light and cosmic rays break apart simpler substances and reassemble them into larger chains. Scientists suspect that comets like this one carry prebiotic chemistry, the raw ingredients from which life might eventually emerge on distant worlds. It took billions of years for these molecules to arrive here, drifting through the galaxy's spiral arms, surviving shockwaves from supernovae, persisting through the long dark between stellar nurseries. The comet does not know it is being observed. Instruments on Earth and aboard spacecraft scattered through the inner solar system track its trajectory with precision. They measure its brightness, analyze the light reflecting from its surface, search for the first signs of activity. Because even though the comet remains far from the sun, the warming has already begun. At these distances, sunlight is weak, only a fraction of what Earth receives, but it is enough. The surface temperature, once hovering near 30 Kelvin, begins to rise. 50 Kelvin. 70. At around 100 Kelvin, carbon monoxide ice starts to sublimate, transitioning directly from solid to gas without passing through a liquid phase. It is a process so gradual that no eye could witness it, yet instruments designed for such subtlety detect the change. A faint haze appears around the nucleus, invisible to human vision but apparent in infrared wavelengths. This is the beginning of the coma, the comet's temporary atmosphere. Gas molecules escape from the surface, freed from their frozen prison, expanding outward into vacuum. They carry with them tiny dust grains that were embedded in the ice, particles smaller than the width of a human hair. These grains scatter sunlight, creating a diffuse glow that extends thousands of kilometers in all directions. The coma grows slowly, fed by sublimation that accelerates as the comet continues its inward journey. Within weeks, the coma will span a volume larger than Jupiter. Though its total mass remains negligible, less than the air in an average-sized room, there is something quietly absurd about this. An object that spent millions of years in silence, traveling through the empty spaces between stars, now announces itself with exhalations of gas and dust. Only took a few million years to make an entrance. The comet itself remains indifferent, governed entirely by physics, by temperature gradients, vapor pressure, and gravitational acceleration. It does not choose to outgas. It simply warms. Scientists study the composition of the coma using spectroscopy, breaking the reflected and emitted light into its constituent wavelengths. Each molecule absorbs and emits light at characteristic frequencies, leaving fingerprints in the spectrum. Early observations reveal water vapor, as expected, but also unexpected abundances of carbon monoxide and nitrogen-bearing compounds. The ratios differ from those seen in comets born within the solar system, hinting at formation conditions in another stellar neighborhood under different pressures and temperatures. Exactly where this comet originated remains a mystery. The Oort cloud. The vast spherical shell of icy bodies surrounding the Sun contains both objects native to the solar system and those captured from interstellar space over billions of years. Distinguishing between the two requires careful analysis, and even then, certainty eludes. As the coma expands, it begins to interact with its environment. Space is not truly empty. Even in the regions between planets, there exists a tenuous medium, the solar wind, a continuous outflow of charged particles from the Sun's corona. This wind flows at speeds between 300 and 800 kilometers per second, carrying with it the Sun's magnetic field, stretched and twisted into a complex structure called the interplanetary magnetic field. The solar wind fills the heliosphere, a bubble of solar influence extending far beyond the planets, into the realm where interstellar space begins. The comet, with its growing coma, represents an obstacle to this flow. Gas molecules released from the nucleus are neutral at first, electrically balanced with equal numbers of protons and electrons, but ultraviolet light from the Sun quickly ionizes them, stripping away electrons and creating positively charged ions. These ions respond to magnetic fields. They cannot simply drift through the solar wind as neutral molecules might. Instead, they are picked up, accelerated, and carried along by the moving plasma. The process is not gentle. It is a collision between two states of matter, the comet's slow exhalation and the Sun's relentless outward breath. Instruments aboard distant spacecraft begin to notice something unusual. The solar wind, which normally flows with relative uniformity at these distances, shows fluctuations. Density increases briefly. Velocity drops. Magnetic field lines kink and twist in ways not predicted by standard models. The comet, still millions of kilometers from perihelion, is already leaving its mark. Only a few kilometers of ice, and already the Sun's river bends. The heliosphere, vast beyond comprehension, adjusts itself around this tiny visitor. And the comet, tumbling in darkness, continues to warm. The nucleus itself is a museum of deep time. Within its ice, preserved as if in amber, are materials that have remained chemically unchanged since before the Sun ignited. When the solar system was only a rotating disk of gas and dust, 4.5 billion years ago, The region beyond Neptune remained cold enough for volatile compounds to freeze. Water ice, of course, but also methane, ammonia, and more exotic substances clathrates, where gas molecules are caged within crystalline water structures, preserved under pressure. These ices accumulated slowly, grain by grain, building bodies that would become comets. But 3I Atlas is different. Its trajectory, when calculated backward through time, does not originate within the solar system's planetary disk. The orbital parameters are wrong, the inclination too steep, the eccentricity too extreme. This comet arrived from somewhere else, carrying ice formed in another star's nebula, under different conditions of temperature, radiation, and chemistry. The precise differences remain subtle, detectable only through careful spectroscopic analysis, but they are their isotopic ratios that do not quite match, abundances of trace molecules that deviate from solar system norms. Scientists describe these objects as time capsules, and the phrase is accurate but also insufficient. A time capsule is intentionally sealed, meant to be opened. The comet preserves nothing deliberately, it simply froze, remained frozen, and now, by accident of trajectory, crosses paths with the Sun and begins to thaw. The information it contains about the early universe is incidental, a byproduct of chemistry and circumstance. Only took 4 billion years for anyone to notice. The surface of the nucleus is not smooth. Sublimation does not proceed uniformly. Where sunlight strikes directly, ices vaporize more rapidly, creating pits and valleys. Where shadows persist, ice remains intact, forming cliffs and overhangs. Over multiple orbits if the comet were to make multiple orbits, which 3I Atlas will not. These features would evolve, the landscape gradually eroding away until nothing remained but refractory dust and rock. But this is the comet's first passage through the inner solar system, at least in recent epochs, and its surface still retains most of its original volatile inventory. Embedded in the ice are dust grains, particles that formed in the atmospheres of dying stars and were expelled into space. When massive stars reach the end of their lives, their outer layers expand and cool, creating conditions where atoms can condense into solid particles, silicates, carbonaceous material, tiny crystals of various minerals. These grains drift through the interstellar medium, sometimes for millions of years, until they encounter a molecular cloud and become incorporated into the next generation of star formation. Some of the grains in 3I Atlas may have originated in stars that died before the Sun was born, making them not just ancient but pre-solar, older than the Earth, older than any rock in the solar system. When the comet outgases, these grains are released along with the vapor. They are too small to fall back to the surface. The nucleus has almost no gravity, so they drift outward, pushed by the pressure of sunlight itself. Photons carry momentum, and when they strike a dust grain and are absorbed or reflected, they transfer that momentum, exerting a tiny but persistent force. Over time, this radiation pressure pushes the dust grains away from the Sun, creating the comet's dust tail, a separate structure from the ion tail. The two tails often point in slightly different directions because they are shaped by different forces. The dust tail follows the comet's orbital path, curved by the grain's initial velocity, while the ion tail points directly away from the Sun, dragged by the solar wind. The dust grains themselves are not inert. Their surfaces are coated with organic molecules, carbon chains, sometimes ringed structures like polycyclic aromatic hydrocarbons. When ultraviolet light from the Sun strikes these molecules, it can break chemical bonds, creating reactive fragments called radicals. These radicals can recombine in new ways, forming more complex molecules. In the diffuse environment of the coma, where densities are extraordinarily low, chemistry proceeds at a glacial pace, but it proceeds nonetheless. Laboratory experiments have shown that similar processes, given enough time, can produce amino acids and other prebiotic compounds. Whether such synthesis actually occurs in comet comae remains an open question. One of those quiet mysteries that persist at the edges of what instruments can detect. As the comet continues inward, the rate of sublimation increases. At 4 astronomical units from the Sun 4 times. The Earth-Sun distance water ice begins to sublimate in addition to the more volatile carbon monoxide. Water vapor becomes the dominant component of the coma, and the outgassing rate jumps by an order of magnitude. The coma expands to hundreds of thousands of kilometers in diameter, though it remains nearly invisible to the naked eye. Only through long-exposure photography or sensitive instruments can its full extent be appreciated. To an observer on Earth, if they could see it at all, the comet would appear as a faint smudge, indistinct, easily overlooked. Yet the comet's influence extends far beyond what is visible. The gas and dust it releases do not simply dissipate into space. They interact with the solar wind, and this interaction creates structures. The first of these is the bow shock, a region where the solar wind encounters the obstacle of the comet's ionosphere and begins to slow down. Just as air flowing past an airplane wing creates turbulence and pressure waves, the solar wind flowing past the comet creates a shock, front, a boundary where plasma transitions abruptly from supersonic to subsonic speeds, from ordered flow to chaotic turbulence. The bow shock forms at a distance of tens of thousands of kilometers from the nucleus, well within the coma but still far from the solid surface. Its exact position fluctuates depending on the solar wind's density and velocity, which vary continuously. Sometimes the shock strengthens and moves closer to the nucleus. Other times, it weakens and recedes. Spacecraft that have flown through comet bow shocks have measured these fluctuations directly, recording rapid changes in magnetic field strength, plasma temperature, and particle density. The data reveal a boundary that is not a simple surface, but a dynamic, turbulent zone where multiple physical processes compete and interact. Scientists have known about comet bow shocks since the 1980s, when the first spacecraft encountered Comet Halley, but each new comet provides additional data, and 3i Atlas, with its interstellar origin, offers a rare opportunity. Do comets from beyond the solar system produce bow shocks with different characteristics? Do variations in chemical composition affect the interaction? Early observations suggest subtle differences, but distinguishing genuine anomalies from normal variability requires careful statistical analysis. Only a few dozen comets have been studied in such detail, and 3i Atlas is the first interstellar visitor to be observed with modern instrumentation. The comet does not care about these distinctions. It continues to outgas, continues to warm, continues its long fall toward the sun. Only a visitor passing through, and already the scientists scramble. The universe, as always, offers no commentary. It simply unfolds, governed by equations that describe but do not explain, by processes that occur whether or not anyone is watching. Sublimation is a word that sounds gentle, almost poetic, but the process itself operates at molecular scales where gentleness has no meaning. A water molecule embedded in the comet's ice lattice vibrates in place, held by hydrogen bonds to neighboring molecules. As temperature rises, the vibration amplitude increases. Eventually, the molecule gains enough kinetic energy to break free from the lattice entirely. It escapes into the void above the surface, joining trillions of other molecules doing the same thing at the same moment across different regions of the nucleus. The transition from solid to gas occurs without any liquid intermediate. On Earth, water melts before it evaporates, but that requires atmospheric pressure. The comet's surface experiences near vacuum conditions, pressures 1 billion times lower than Earth's atmosphere. At such pressures, liquid water cannot exist. The phase diagram for water shows a boundary below which the liquid state is thermodynamically forbidden. The comet operates entirely below that boundary, so ice becomes vapor directly, a transition marked by the absorption of latent heat. This heat must come from somewhere. Solar radiation provides most of it, photons arriving at the speed of light and being absorbed by the dark surface material. The surface heats up, and that thermal energy propagates inward through the ice. Though very slowly, ice is a poor conductor of heat. Beneath the surface, perhaps only centimeters or meters down, temperatures remain at their original frigid levels, unchanged by the sun's influence. The comet is thus divided into 2 regimes, a thin, active layer that responds to sunlight, and a deep interior that remains in thermal equilibrium with deep space. The molecules that escape carry momentum. They do not simply drift away passively, they are expelled with velocities of hundreds of meters per second, determined by the surface temperature. These velocities are far below the escape velocity needed to leave the comet's gravity well, which is negligible anyway, measured in centimeters per second for a body this small. So the molecules fly outward freely, expanding into the growing coma. They travel in straight lines until they collide with other molecules or are ionized by ultraviolet radiation, processes that occur at different rates depending on the local density and the intensity of sunlight. The coma that results is not uniform. Regions closer to the nucleus have higher densities, while the outer regions are more diffuse. The distribution follows an inverse square law, diluting rapidly with distance. At the nuclear surface, densities might reach 10 billion molecules per cubic centimeter, still 1 million times more rarefied than Earth's atmosphere. But substantial by space standards, 1,000 kilometers away, densities drop to perhaps 10 million molecules per cubic centimeter. 10,000 kilometers out. Maybe 10,000. The coma extends far beyond where densities can be reliably measured, fading asymptotically into the background interplanetary medium. Within this expanding cloud, chemistry unfolds. Parent molecules, the compounds that sublimate directly from the ice, begin to break apart under ultraviolet bombardment. Water molecules split into hydrogen and hydroxyl radicals. Carbon dioxide becomes carbon monoxide and oxygen. Ammonia loses hydrogen atoms one by one. These daughter molecules then undergo further reactions, creating a cascade of increasingly complex chemistry. Exactly which products form, and in what abundances, depends on the local radiation field, the densities involved, and the timescales available before the molecules drift too far apart to interact. Scientists observe this chemistry remotely by detecting the characteristic wavelengths emitted when molecules transition between energy states. Each molecular species has a unique spectral signature. By comparing observed spectra to laboratory measurements, researchers can identify what molecules are present and estimate their abundances. This is how we know, for instance, that 3I Atlas contains unusually high concentrations of carbon monoxide relative to water, a ratio different from most solar system comets, consistent with formation in a colder environment where carbon monoxide ice could condense more readily. But there are limits to what can be determined from Earth. The coma is optically thin, meaning light passes through it with minimal scattering. So spectroscopic observations integrate emission along the entire line of sight. Distinguishing between molecules near the nucleus and those farther out requires modeling. Assumptions about the outflow velocity and the photodissociation rates. These models are sophisticated, built on decades of research, but they remain models' approximations of reality constrained by incomplete data. Actual conditions within the coma, especially close to the nucleus where densities are highest, remain somewhat mysterious. Spacecraft missions have provided ground truth for a handful of comets, flying close enough to sample the coma directly with mass spectrometers and other instruments. These missions revealed unexpected complexity variations in composition across the nucleus surface, jets of gas erupting from specific locations, diurnal changes as the comet rotates, and different regions enter or exit sunlight. 3I Atlas will not receive such a visit. It appeared too suddenly. Its interstellar nature recognized too late to organize a mission, so it remains an object of remote study. Knowable only through the light it reflects and emits, through the perturbations it creates in the solar wind, and those perturbations are becoming more pronounced. As the coma grows, as more gas is released and ionized, the comet's interaction with the solar wind intensifies. The ions created by photoionization, mostly water group ions, with smaller contributions from carbon monoxide and other species, are immediately picked up by the solar wind's magnetic field. This pickup process is not gradual. An ion, newly created and initially at rest in the comet's frame of reference, suddenly finds itself immersed in a magnetic field moving at hundreds of kilometers per second. The field exerts a force, accelerating the ion perpendicular to both the field direction and the direction of motion. The result is a helical trajectory, the ion spiraling around magnetic field lines as it is swept away from the comet. But the ion's mass does not disappear. It is added to the solar wind plasma, increasing the local density. To conserve momentum, the solar wind must slow down slightly. For a single ion, the effect is negligible. For the trillions of ions produced every second as 3I Atlas outgases, the cumulative effect becomes measurable. The solar wind begins to decelerate well before it reaches the bow shock, responding to the distributed load of newly picked up ions. This mass loading, as it is called, creates instabilities in the plasma. The picked-up ions have different velocities and temperatures than the background solar wind, creating a population of energetic particles that can drive waves and turbulence. Magnetic field lines kink and oscillate. Density fluctuations propagate through the plasma at the Alf-Venn speed, a characteristic velocity determined by the magnetic field, strength, and the plasma density. These waves can accelerate particles to even higher energies, creating a feedback loop where instability begets more instability. Only a cloud of gas, and the solar wind starts to stutter. The heliosphere, ordinarily so uniform, develops wrinkles, and the comet, indifferent, continues to sublimate, continues to release ancient ice into the void, molecule by molecule, grain by grain, as it has done for weeks now and will continue to do for weeks to come. The solar wind itself is an old discovery that still holds mysteries. In the 1950s, scientists debated whether space between the planets was truly empty or filled with some tenuous medium. Eugene Parker, then a young physicist, proposed that the sun's corona, its outer atmosphere, was so hot that it could not remain gravitationally bound. Instead, it must expand continuously outward, creating a supersonic flow of plasma that pervades the entire solar system. The idea met with skepticism. Referees rejected his paper. Only the intervention of an editor allowed it to be published, and, even then, many researchers dismissed it as speculative. But Parker was correct. Spacecraft launched in the following decades confirmed the solar wind's existence, measured its properties, tracked its variations. The wind originates in the corona, where temperatures reach 1 to 2 million Kelvin, hot enough that hydrogen atoms are fully ionized, existing as free protons and electrons. These particles, thermally agitated, move at speeds of hundreds of kilometers per second. The sun's gravity tries to hold them, but thermal pressure overwhelms gravitational attraction. The plasma expands, accelerating as it flows outward through the sun's magnetic field. The wind is not uniform. It emerges faster from coronal holes regions where magnetic field lines are open, extending into space rather than looping back to the solar surface. In these regions, wind speeds can exceed 800 kilometers per second. Elsewhere, where the corona is denser and more magnetically complex, the wind flows more slowly, perhaps 300 to 400 kilometers per second. The boundary between fast and slow wind creates shear layers, regions of enhanced turbulence where the two streams interact. Embedded in this flow is the sun's magnetic field, dragged outward by the moving plasma. In ideal magnetohydrodynamics, the theoretical framework used to describe plasma behavior, magnetic field lines are said to be frozen into the plasma, meaning the field and the plasma move together, inseparable. This frozen-in condition creates a peculiar geometry. As the sun rotates, the field lines connected to the rotating surface are drawn out into spirals, like water streaming from a rotating sprinkler. The resulting pattern is called the Parker spiral, a structure that extends throughout the heliosphere, its pitch angle depending on the radial distance from the sun and the solar wind speed. At Earth's orbit, the field is neither radial nor tangential, but somewhere in between, making an angle of about 45 degrees with the radial direction. Farther out, the spiral winds more tightly. Closer in, the field is more nearly radial. The comet, currently several astronomical units from the sun, encounters a field that is already significantly spiral, twisted by the sun's 27-day rotation period. This field will drape over the comet, conforming to the obstacle, creating a complex magnetic topology. The solar wind also carries kinetic energy from its bulk motion, thermal energy from the random motions of individual particles, and magnetic energy stored in the field. Energy densities are low by terrestrial standards, but integrated over the vast volume of the heliosphere, the total energy flux is enormous, equivalent to the output of millions of power plants running continuously. Most of this energy simply flows outward into interstellar space, lost forever as the heliosphere expands. But some of it is tapped by processes within the heliosphere, by planets with magnetospheres, by comets with ionospheres, by shock waves and magnetic reconnection events. The solar wind also varies with time. The sun's activity follows an 11-year cycle, during which the number of sunspots, the frequency of solar flares, and the structure of the corona all change. At solar maximum, the corona is complex and dynamic, with coronal mass ejections, vast eruptions of plasma occurring frequently. At solar minimum, the corona is quieter, more structured, with well-defined coronal holes. These variations affect the solar wind at all distances, causing the wind's density, velocity, and magnetic field strength to fluctuate on timescales ranging from minutes to years. Currently, the sun is in a moderately active phase, neither at maximum nor minimum. Coronal mass ejections occur every few days, sending pulses of high-density plasma outward through the solar system. When these pulses encounter the comet, they compress the coma, strengthen the bow shock, and intensify the interaction. Instruments monitoring the solar wind near Earth detect these events and can predict, with some uncertainty, when they will reach the comet's location. The predictions are imperfect. The solar wind is turbulent, and conditions can change unpredictably, but they provide context for interpreting observations of the comet. The comet, for its part, does not respond uniformly to these variations. Its outgassing rate depends primarily on sunlight, which varies smoothly with distance and only slightly with the sun's activity. But the interaction with the solar wind, the bow shock formation, the ion pickup, the magnetic draping is sensitive to the wind's properties. When a dense, fast-moving coronal mass ejection sweeps past the comet, the bow shock strengthens and moves closer to the nucleus. The ion tail brightens as more ions are accelerated. Magnetic field lines compress and reconnect more frequently. Then, as the pulse passes and conditions return to baseline, the interaction relaxes. Scientists have observed such transient events at other comets and found them rich with physics. Magnetic reconnection, a process where oppositely directed field lines break and rejoin. Releasing energy occurs frequently in the turbulent environment downstream of the bow shock. These reconnection events accelerate particles to high energies, sometimes creating bursts of X-rays as energetic electrons collide with neutral gas in the coma. The X-ray emission from comets was itself a surprise when first discovered in the 1990s. Unexpected because comets are cold objects that emit primarily at infrared and visible wavelengths. Only the interaction with the solar wind, only the energy available in the wind's magnetic field, makes X-ray emission possible. At 3I Atlas, these processes are underway. The comet's interstellar origin does not exempt it from the physics governing all comet-solar wind interactions. The same mechanisms operate ionization, pickup, magnetic draping, reconnection, but the details matter. The composition of the coma, with its elevated carbon monoxide abundance, may affect ionization rates. The comet's relatively low activity level, it is a small object, outgassing less vigorously than larger. More active comets may influence the bow shock's structure. These are subtle effects, difficult to disentangle from the natural variability of the solar wind itself. Only a few spacecraft in the right positions, and already the data accumulate. Measurements of plasma density, magnetic field vectors, energetic particle fluxes, the numbers pile up, awaiting analysis, interpretation, the slow construction of understanding from fragments. And the solar wind flows onward, indifferent to the comet, indifferent to the scientists, carrying the sun's magnetic field into the dark. The bow shock that forms around the comet is not a solid boundary. It is a statistical phenomenon, a region where the probability of particle collisions and wave-particle interactions increases sharply. In ordinary circumstances, the solar wind plasma is collisionless particles travel vast distances without directly striking one another because the density is so low. A cubic centimeter of solar wind at Earth's orbit contains only a few protons and electrons, separated by distances far larger than their physical sizes. Collisions, in the classical sense of billiard balls striking each other, almost never occur. Yet the plasma behaves as if it were collisional. Particles scatter, energies thermalize, shock waves form. This apparent paradox is resolved by recognizing that electromagnetic forces mediate the interactions. Charged particles generate electric and magnetic fields, and these fields affect other charged particles at a distance. Waves propagate through the plasma, carrying information about density fluctuations and field perturbations. Through these collective effects, the plasma can act like a fluid despite the absence of direct collisions. The bow shock is a place where these collective effects dominate. As the solar wind approaches the comet, it encounters the cloud of ions being picked up from the coma. These ions, as mentioned, are initially at rest in the comet's frame, but are then accelerated by the solar wind's magnetic field. The acceleration is not instantaneous. The ions gyrate around field lines, gaining velocity perpendicular to the field direction while being swept along parallel to the flow. This creates a ring beam distribution in velocity space, a population of ions moving in a ring around the background field direction. Ring beam distributions are unstable. They possess free energy that can drive plasma waves. The waves grow, extracting energy from the ion distribution, and in turn scatter the ions, spreading them out in velocity space until the distribution becomes more isotropic. This process, happening continuously as new ions are picked up, generates turbulence that heats the plasma and slows the solar wind. The deceleration is gradual at first, occurring over large distances upstream of the comet, but as the ion density increases closer to the nucleus, the deceleration intensifies. Eventually, the solar wind slows to the point where its velocity equals the local wave speed specifically, the magnetosonic speed, which depends on both the plasma temperature and the magnetic field strength. At this critical point, the flow transitions from supersonic to subsonic, and a shock forms. The shock is a thin region, perhaps only a few hundred kilometers thick, where plasma properties change abruptly. Upstream, the flow is fast, cool, and relatively uniform. Downstream, the flow is slower, hotter, and more turbulent. The transition is not smooth but marked by oscillations and fluctuations as the shock adjusts to varying upstream conditions. The exact position of the bow shock depends on a balance between the solar wind's dynamic pressure and the pressure exerted by the comet's ionosphere. When the solar wind is strong, the shock moves closer to the nucleus. When the comet's outgassing increases, the ionosphere expands and pushes the shock farther out. This balance is never static. The solar wind's density and velocity vary continuously, and the comet's outgassing rate changes as different regions of the nucleus enter or exit sunlight. The shock's position fluctuates by thousands of kilometers over timescales of hours to days. Spacecraft that have crossed comet bow shocks report the crossing as a series of rapid changes in measured quantities. Magnetic field strength jumps by a factor of 2 or 3. Plasma density spikes, temperature increases. Particle detectors register bursts of energetic ions and electrons. Then, within minutes, the spacecraft exits the shock region, entering the downstream environment where conditions are different but still turbulent. Some spacecraft have crossed the same shock multiple times as it moved back and forth, providing repeated measurements of the same boundary from different perspectives. At 3i Atlas, no spacecraft is nearby to make such direct measurements. The interaction must be inferred from remote observations and from monitoring stations scattered elsewhere in the solar system. Spacecraft near Earth, for instance, can detect disturbances in the solar wind that may have originated at the comet. Magnetic field perturbations, propagating outward as Alfvén waves, can travel across millions of kilometers before dissipating. By triangulating observations from multiple spacecraft, researchers can sometimes trace these perturbations back to their source. The process is imperfect. The heliosphere is filled with transient structures, shocks from coronal mass ejections, stream interaction regions where fast and slow solar wind collide, corrotating interaction regions tied to the sun's rotation. Distinguishing the comet's influence from this background noise requires careful analysis and often leaves ambiguities unresolved. A particular fluctuation in the magnetic field, is it from the comet or from a small-scale solar wind structure that passed the monitoring spacecraft? The data alone cannot always answer, yet patterns emerge over weeks of observation. As the comet brightens and its outgassing increases, the frequency of certain types of perturbations in the solar wind also increases. statistical correlations appear, suggesting a connection even if individual events remain ambiguous. This is how science often proceeds, not with definitive proof from a single observation, but with the accumulation of evidence, the slow convergence toward understanding through multiple lines of reasoning. The comet's bow shock, like all shocks, is a dissipative structure. It converts the ordered kinetic energy of the solar wind's bulk flow into disordered thermal energy, heating the plasma. The second law of thermodynamics ensures that this process is irreversible. Entropy increases. The solar wind emerging downstream from the shock is degraded, in a thermodynamic sense, relative to the pristine wind that approached. Some of the wind's kinetic energy has been permanently converted into heat, which will eventually radiate away into space as photons, lost forever. This energy conversion is not unique to comets. It occurs at Earth's bow shock, at the bow shocks of other planets with magnetospheres, at interplanetary shocks driven by coronal mass ejections. It is a fundamental aspect of how plasmas interact with obstacles. The comet simply provides another example, another laboratory where the same physics plays out in slightly different circumstances. Only a small visitor, and already it heats the sun's wind. The energy is negligible compared to the solar wind's total flux, but locally, at the shock, it matters. Particles gain energy, waves are generated, entropy increases. The universe, as always, moves toward disorder, one interaction at a time. Downstream from the bow shock lies a region called the magnetosheath, though for a comet, the term is somewhat misleading, as comets do not possess intrinsic magnetic fields like planets do. The word persists from planetary physics, where the magnetosheath is the turbulent layer between a planet's bow shock and its magnetopause. For comets, there is no magnetopause, no sharp boundary where the solar wind's magnetic field is excluded. Instead, the field drapes over the ionosphere, conforming to the obstacle's shape, creating a more gradual transition. The draping process is elegant in its geometry. Magnetic field lines carried by the solar wind cannot penetrate into regions of high electrical conductivity, a consequence of Faraday's law of induction. The comet's ionosphere, though tenuous, is sufficiently conductive to exclude most of the solar wind's field. As field lines approach the ionosphere, they are deflected around it, stretching and bending to accommodate the obstacle. The result is a draped configuration, with field lines hugging the ionosphere's boundary and extending downstream in the anti-sunward direction. This draped field creates a magnetic tail, distinct from the visible ion tail but occupying the same general region of space. The tail is structured, with field lines that entered the interaction region from opposite sides of the comet forming separate lobes. Between these lobes lies a current sheet, a thin layer where the magnetic field reverses direction and electric currents flow. The current sheet is a site of intense activity. Magnetic reconnection occurs here frequently, driven by the anti-parallel field geometry and the turbulence inherited from the bow shock crossing. When reconnection occurs, field lines from opposite lobes merge, forming closed loops that detach and move downstream, away from the comet. Plasma trapped on these closed loops is released, accelerated by the magnetic tension as the field lines snap back toward a lower energy configuration. This process contributes to the ion tail's dynamics, helping to sweep ions away from the comet and into the distant solar wind. It also releases energy, heating the plasma locally and generating bursts of waves that propagate both upstream and downstream. Scientists have observed these reconnection events at several comets, using both spacecraft data and remote optical observations. The ion tail brightens periodically, displaying knots and disconnections where segments of the tail separate from the coma and drift away. These disconnection events correlate with sudden changes in the solar wind's magnetic field direction, particularly when the interplanetary field rotates such that its orientation becomes unfavorable for maintaining the draped configuration. The tail disconnects, a new tail begins to form, and the cycle repeats. At 3I Atlas, such events are expected but not yet prominently observed. The comet's tail remains faint, visible only through long exposures and image processing. Still, spectroscopic observations reveal variability in the tail's brightness and in the emission from certain ions, suggesting that dynamic processes are underway. The temporal resolution of these observations is limited. Most are taken hours or days apart, so rapid fluctuations may go undetected. Only continuous monitoring, ideally from multiple observatories, could capture the full range of variability. The draped magnetic field also affects how the solar wind flows around the comet. In ideal magnetohydrodynamics, the plasma and field must move together, so the field's geometry constrains the flow. Where field lines drape closely around the ionosphere, the plasma is deflected, channeled into narrow streams that accelerate as they pass the obstacle. Where field lines stretch into the tail, the plasma flows more slowly, filling the wake region behind the comet. This wake is not empty. It contains plasma, both solar wind material that has been slowed and heated, and ions picked up from the coma. The two populations mix, but imperfectly. The picked-up ions have lower bulk velocities, having been accelerated only recently, while the solar wind ions retain much of their original speed despite the bow-shock crossing. The velocity difference creates shear, and shear drives instabilities, generating waves that scatter particles and mix the populations over time. The magnetic field within the wake is weaker than in the surrounding solar wind, a consequence of the draping and the exclusion from the ionosphere. Field strength might drop by a factor of 2 or more, though exact values depend on the local plasma conditions. This reduction in field strength affects the Alfvén speed, which in turn affects how waves propagate. Waves that could travel freely in the ambient solar wind may be refracted or reflected at the wake boundary, creating complex patterns of interference. Dust grains released by the comet also accumulate in the wake, though they follow different trajectories than the gas. Dust is not ionized, so it does not respond to magnetic fields. Instead, it responds to radiation pressure and gravity. Small grains, less than a micrometer in size, are pushed outward by sunlight faster than they are pulled inward by the comet's negligible gravity or the sun's distant pull. Larger grains, less affected by radiation pressure, drift more slowly. The size distribution of the grains thus determines the spatial distribution of the dust tail. Observations of the dust tail provide information about this size distribution. By measuring how the tail's brightness varies with the distance from the nucleus and how the tail's shape changes over time, researchers can infer the sizes and velocities of the grains. Models are constructed, parameterized by grain size, composition, and emission velocity, and fitted to the observations. The best fit models provide estimates of the dust production rate and the grain size distribution, though significant uncertainties remain. At 3I Atlas, preliminary models suggest a dust-to-gas ratio lower than typical for solar system comets. This means the comet is releasing proportionally less dust relative to gas, possibly because its ice is less contaminated with refractory material, or because the grains that are present are small and difficult to detect. The ratio may also change as the comet approaches perihelion and different ice reservoirs become active. More observations are needed to constrain the models. The wake extends far downstream, potentially millions of kilometers, though it gradually dissipates as the disturbed plasma mixes with the ambient solar wind. At great distances, the comet's influence becomes indistinguishable from background fluctuations. The solar wind resumes its normal flow, erasing the memory of the interaction. Only in the immediate vicinity of the comet does the perturbation remain strong, localized, measurable, only a temporary disturbance, and already it fades. The heliosphere absorbs the comet's presence, accommodates it, and moves on. The magnetic field lines straighten, the plasma re-accelerates, the turbulence decays, and the comet continues inward, leaving a wake that stretches and thins, becoming less distinct with every passing hour. The ion tail itself is a structure of surpassing delicacy. From Earth, through telescopes equipped with filters that isolate specific emission wavelengths, it appears as a faint blue streak extending millions of kilometers into space. The blue color comes primarily from ionized carbon monoxide CO+, which emits strongly in the ultraviolet and blue portions of the spectrum when electrons recombine with ions or when ions are excited by solar radiation. Water group ions, particularly H2O+ and OH+, also contribute, emitting at slightly different wavelengths that can be distinguished spectroscopically. The tail always points away from the sun, a fact noted by astronomers for centuries before the physical mechanism was understood. In the 16th century, observers recorded that comet tails seemed to flee from the sun, as if repelled by some invisible force. The true explanation that charged particles are swept downstream by the solar wind was not recognized until the mid-20th century, after the solar wind's existence was confirmed. Even then, the full complexity of the interaction remained obscure until spacecraft could measure conditions in situ. The ions that form the tail originate in the coma through photoionization, ultraviolet photons from the sun, particularly those at wavelengths shorter than about 100 nanometers, carry enough energy to strip electrons from neutral molecules. The ionization rate depends on the photon flux and on the molecule's ionization cross-section, a measure of how likely a given molecule is to be ionized when struck by a photon. Water has a relatively low ionization cross-section, while carbon monoxide's is somewhat higher. The differences are modest, but they affect the relative abundances of ions in the tail. Once ionized, a molecule becomes subject to electromagnetic forces. The solar wind's electric field, induced by the motion of the magnetized plasma, accelerates ions in the anti-sunward direction. The magnetic field constrains the ions to gyrate around field lines while being carried along with the flow. The combination produces a net motion away from the sun, though the trajectory is not perfectly radial. Ions are also affected by the draped field geometry near the comet, which can deflect them in various directions depending on their position within the coma. The ion tail is not static. It evolves continuously as new ions are created near the nucleus and old ions are swept far downstream. The tail's brightness at any given location depends on the local ion density and the excitation state of those ions. Regions where ions are freshly accelerated may glow more brightly due to collisional excitation. Regions farther downstream, where ions have thermalized and the plasma has rarefied, may be dimmer. Time-lapse images of comets often reveal waves or kinks propagating along the tail, visible manifestations of magnetohydrodynamic disturbances. These waves can be driven by several mechanisms. Variations in the solar wind's velocity or magnetic field orientation can create pulses that travel down the tail at the local Alfvén speed. Reconnection events in the magnetic tail as previously mentioned, can release plasmoids, detached loops of magnetic field containing trapped plasma that move downstream as coherent structures. Instabilities at the boundary between the tail and the ambient solar wind can generate vortices and turbulence that modulate the tail's appearance. At 3 the Atlas, the ion tail is still developing. The comet is not yet at perihelion, not yet at maximum activity, so the tail remains relatively short and faint compared to what it will become in the coming weeks. Observations show a narrow structure, perhaps 500,000 kilometers long, with only subtle brightness variations along its length. No major disconnection events have been recorded, though this may simply reflect the limited cadence of observations rather than an absence of such events. Spectroscopic analysis of the tail reveals emission lines from CO+, as expected given the coma's composition, but also weaker lines from other species CN+, N2+, and various water group ions. The relative strengths of these lines provide clues about the coma's chemistry and the ionization processes at work. By comparing observed line ratios to theoretical predictions, researchers can test models of how molecules are destroyed and ionized in the comet's environment. One puzzle that persists across comet observations is the temperature of the ions in the tail. Measurements, when available, often indicate temperatures much higher than would be expected from simple photoionization followed by solar wind pickup. The excess temperature suggests additional heating mechanisms, perhaps wave-particle interactions, or acceleration at the bow shock, or reconnection-driven heating in the magnetic tail. Exactly which mechanism dominates, and under what conditions, remains an area of active research. The ion tail also carries information about the solar wind itself. Because the ions are picked up directly from the coma and then swept into the tail, their trajectories trace the solar wind's flow pattern. By observing how the tail's orientation changes over time, astronomers can infer changes in the solar wind direction at the comet's location. This makes comets useful as remote probes of solar wind conditions in regions of space where no spacecraft are present. At 3I Atlas, this technique reveals a relatively steady solar wind direction over the past several days, consistent with measurements from spacecraft elsewhere in the solar system. The tail points consistently anti-sunward with only minor deviations, suggesting that the interplanetary magnetic field direction has not undergone any large-scale rotations recently. This stability is somewhat fortunate. It simplifies the interpretation of other observations and reduces the likelihood of major tail disconnection events that could complicate the data. The dust tail, by contrast, is more curved, following the comet's orbital path rather than the instantaneous solar wind direction. Because dust grains are not ionized, they are pushed by radiation pressure but not by the solar wind's magnetic field. Their trajectories depend on their initial velocities when released from the nucleus, their sizes, and the balance between solar radiation pressure and gravity. Smaller grains are pushed more effectively and form a straighter tail. Larger grains, less affected by radiation pressure, follow more curved paths, creating a broad, fan-shaped structure. The two tails, ion and dust, sometimes appear as distinct features in images. The ion tail narrow and straight, the dust tail broad and curved. At other times, particularly when the comet is faint or the observing geometry is unfavorable, the two tails blend together, indistinguishable without spectroscopic or polarimetric analysis. At 3I Atlas, the dust tail is even fainter than the ion tail, barely detected above the background sky brightness. So most attention has focused on the ion tail as the more readily observable feature. Only light and plasma, and already a tail spans the void. Millions of kilometers of near emptiness, populated by ions too sparse to affect anything beyond their immediate vicinity, yet visible across interplanetary distances when enough of them emit coherently. The universe, once again, makes visible what should be invisible, drawing attention to the tenuous and the transient. Spacecraft monitoring the solar wind from various locations in the inner heliosphere begin to register subtle anomalies. These are not dramatic events, no sudden shocks, no violent fluctuations, but rather small deviations from the expected baseline. At one monitoring station, positioned sunward of the comet's orbit, the solar wind's proton density increases by about 5% over the course of several hours, then returns to normal. At another station, downstream and slightly off to the side, magnetic field measurements show enhanced variability in the field's transverse components, as if small waves are rippling through the plasma. The anomalies are not initially attributed to the comet. The solar wind is naturally turbulent, filled with structures at all scales, and distinguishing genuine signals from random fluctuations requires statistical rigor. Researchers examining the data apply correlation techniques, searching for patterns that might indicate a common source. They compare timing, account for the travel time of disturbances propagating at the solar wind speed, and check whether the observed features align with the comet's known position and activity level. Gradually, a picture emerges. Some of the observed fluctuations appear to correlate with the comet's location, suggesting that disturbances originating at 3I Atlas are propagating outward through the heliosphere. The correlations are not perfect. There is scatter. There are outliers, but they are statistically significant, unlikely to arise from chance alone. The conclusion, tentative but growing stronger with each day's data, is that the comet is indeed perturbing the solar wind in measurable ways, even at distances of tens of millions of kilometers from the nucleus. The mechanism behind these long-range effects involves waves. When the bow shock forms and ions are picked up, energy is deposited into the plasma in the form of waves specifically. Alpha-Venn waves and magnetosonic waves. These waves propagate away from the disturbance, carrying energy and momentum with them. Alpha-Venn waves, in particular, can travel vast distances in the solar wind with relatively little damping, because the plasma is so tenuous that dissipative processes are weak. Alpha-Venn waves are oscillations in the magnetic field and plasma velocity that propagate along magnetic field lines. They are named after Hannes Alfvén, who predicted their existence in the 1940s based on magnetohydrodynamic theory. The waves travel at the Alfvén speed, which depends on the magnetic field strength and the plasma density. In the solar wind near Earth's orbit, the Alfvén speed is typically a few tens of kilometers per second, much slower than the solar wind's bulk velocity, but still fast enough that waves can traverse the distance from the comet to monitoring spacecraft in a matter of hours or days. The waves generated at the comet are not monochromatic. They span a range of frequencies and wavelengths, reflecting the turbulent, broadband nature of the source. Some wave energy resides in low-frequency fluctuations that oscillate over time scales of minutes. Other energy appears at higher frequencies, periods of seconds or less, detectable only with high-cadence instruments. The wave spectrum carries information about the processes generating the waves, about the pickup ion distribution, the bow shock structure, the reconnection events in the tail. When these waves reach a spacecraft, they produce the observed fluctuations in magnetic field and plasma density. The spacecraft is essentially sampling the wave as it passes, recording the oscillating fields and velocities. By analyzing the wave properties, amplitude, frequency, polarization. Propagation direction. Researchers can infer characteristics of the source region. This is analogous to how seismologists use earthquake waves to probe Earth's interior. Except here, the medium is plasma and the source is a comet. But the interpretation is complicated by the fact that waves interact with the plasma as they propagate. They can be refracted by gradients in Alfvén speed, reflected at boundaries where plasma properties change, or damped by various dissipative mechanisms. Waves can also interact with each other, coupling nonlinearly to produce waves at new frequencies. By the time a wave reaches a distant spacecraft, it may have been significantly modified from its original form at the comet. Despite these complications, patterns can be discerned. The observed waves show characteristics consistent with generation via ion pickup, a certain polarization, a certain relationship between magnetic and velocity fluctuations. The timing aligns with expectations based on the wave travel time from the comet. The amplitude correlates, albeit loosely, with the comet's estimated outgassing rate. None of these pieces of evidence is conclusive alone, but together they build a case that the comet is the source. Still, uncertainties remain. The solar wind itself generates waves through various internal processes, stream interactions, turbulent cascades, instabilities. Disentangling the comet's contribution from this background is difficult. Some researchers argue that the observed correlations could be coincidental, that the waves attributed to the comet might actually originate elsewhere. The debate continues in the literature, as it often does when interpreting complex, multivariate data. What is not in doubt is that the comet's interaction with the solar wind is more complex than early models predicted. Those models, developed decades ago based on a handful of in situ observations at other comets, assumed a relatively simple interaction geometry and neglected many second-order effects. They worked well for large, active comets with strong outgassing, but for a small, moderately active object like 3I Atlas, the assumptions break down. The bow shock is weaker, the mass loading is less intense, and subtle effects previously negligible become important. One such effect involves the finite gyroradius of picked-up ions. When an ion is accelerated by the solar wind's magnetic field, it begins to gyrate around the field line with a characteristic radius determined by its velocity and the field strength. For typical conditions, this gyroradius is tens to hundreds of kilometers. If the gyroradius is comparable to the scale of the interaction region, the ion's trajectory cannot be approximated as following the field line. Instead, the full particle motion must be considered. This complicates the dynamics, introducing kinetic effects that are absent in fluid models. Another subtlety involves the comet's rotation. As the nucleus spins, different regions enter and exit sunlight, causing the outgassing rate to vary periodically. For 3I Atlas, the rotation period is estimated at around 8 hours based on brightness variations. This periodicity imposes a temporal structure on the outgassing, creating a modulated ion source. The modulation propagates through the coma and into the interaction region, potentially affecting the bow shock stability and the wave generation. Detecting this modulation in the solar wind data would provide strong evidence of the comet's influence, but the signal is weak and buried in noise, only a small modulation. And already it challenges detection. The data accumulate, the analysis continues, the uncertainties persist, and the comet, still warming, still outgassing, still falling sunward, remains indifferent to the complexities of interpretation, indifferent to the debates among scientists, indifferent to the waves it sends rippling through the heliosphere. The dust grains themselves, those microscopic fragments liberated from the comet's ice, are more than passive traces. Each grain is a tiny charged object, acquiring electrical potential through interactions with the surrounding plasma and ultraviolet radiation. The charging process is straightforward in principle, but complex in detail. Photons striking the grain can eject electrons via the photoelectric effect. leaving the grain positively charged. Simultaneously, electrons and ions from the plasma collide with the grain, depositing charge. The grain's equilibrium potential is determined by the balance between these processes. For typical solar wind conditions and grain compositions, the equilibrium potential is positive, a few volts relative to the surrounding plasma. This seems modest, but the grains are small, often less than a micrometer in radius, so the electric field at the grain surface can be substantial, millions of volts per meter. This field affects how electrons and ions approach the grain, creating a sheath region around each particle where the plasma properties differ from the ambient values. Charged grains interact with magnetic fields, though much more weakly than ions do. The grain's charge-to-mass ratio is far smaller than an ion's, so the Lorentz force, the force exerted by magnetic fields on moving charged particles, is correspondingly weaker. Still, over long time scales and large distances, the cumulative effect can be measurable. Grains may drift slowly, perpendicular to both the magnetic field and their direction of motion, creating subtle asymmetries in the dust tail's spatial distribution. More importantly, the grains interact with each other electrostatically. A cloud of charged grains generates a collective electric field that can influence the trajectories of nearby grains. If the dust density is high enough, this can lead to collective phenomena, dust acoustic waves, for instance, where compressions and rarefactions propagate through the dust cloud at speeds determined by the grain charge, mass, and number density. Such waves have been observed in laboratory dusty plasmas and inferred in planetary rings, but whether they occur in comet dust tails remains an open question. The grains also act as obstacles to the plasma, analogous to the comet nucleus itself, but on a far smaller scale. Each grain excludes plasma from a volume around it, creating a tiny wake. For an isolated grain, this wake is insignificant. But when billions of grains are present, distributed throughout the coma and tail, the cumulative effect may be detectable as a reduction in plasma density or an enhancement in magnetic field strength, as the field lines are compressed into the regions between grains. Spacecraft that have flown through comet dust tails have detected impacts from these grains, events recorded by dedicated dust detectors. Each impact produces a characteristic signal, a brief pulse of ionization, as the grain vaporizes upon striking the detector at high relative velocity. By analyzing the pulse's amplitude and shape, researchers can estimate the grain's mass and, with additional information, its composition. The data reveal a wide range of grain sizes, from submicron particles to grains hundreds of micrometers across, with compositions dominated by silicates and carbon-rich materials. At 3I Atlas, no spacecraft will pass through the dust tail, so direct measurements are unavailable. Instead, the dust must be studied remotely through its scattering of sunlight. The scattered light's intensity depends on the grain size distribution, the total dust mass, and the scattering properties of the grain material. By observing the dust tail at multiple wavelengths and polarizations, researchers can constrain these parameters, though the constraints are often weak due to the many variables involved. Preliminary observations suggest that the grains from 3I Atlas are smaller on average than those from typical solar system comets. This inference comes from the dust tail's color, slightly bluer than expected, which indicates preferential scattering by small grains. The size distribution may reflect differences in how the ice formed or how it is structured, with less aggregation of small grains into larger ones. Alternatively, it may simply be a selection effect, with larger grains present but not detected due to their lower number density and weaker scattering. The grains continue their outward journey long after leaving the coma. Radiation pressure accelerates them slowly but continuously, pushing them onto hyperbolic trajectories that will carry them out of the solar system entirely. Within thousands of years, the dust from 3I Atlas will be scattered across interstellar space, joining the diffuse medium of dust that pervades the galaxy. Some grains may eventually be incorporated into new molecular clouds, new episodes of star formation, continuing the cycle of matter through the cosmos. But, for now, the grains remain in the sun's vicinity, drifting outward, scattering light, carrying away a small fraction of the comet's original mass. The loss rate is modest, perhaps a few kilograms per second of dust, compared to hundreds of kilograms per second of gas. Over the comet's active lifetime, measured in months, the total dust loss will amount to millions of kilograms, a negligible fraction of the nucleus's total mass, but enough to alter the surface appearance and structure. The grains also carry information about the comet's interior. Because they were embedded in the ice, they record conditions at the time of the comet's formation. Analysis of dust from other comets has revealed pre-solar grains, grains older than the solar system, identifiable by their anomalous isotopic compositions. These grains are tiny time capsules in their own right, preserving information about stellar nucleosynthesis, supernova explosions, and the chemical evolution of the galaxy. Whether 3I Atlas contains pre-solar grains is unknown. The comet's interstellar origin makes it plausible, perhaps even likely. But without direct sample collection and laboratory analysis, confirmation is impossible. Remote observations cannot distinguish pre-solar grains from ordinary grains based on isotopic composition. The spectral resolution is insufficient. This remains one of the many questions that could be answered by a sample return mission, though none is planned for this particular comet. The grains also serve as a reminder of the comet's ephemerality. Each grain released is mass permanently lost, mass that cannot contribute to future outgassing or to the comet's structural integrity. Over multiple passages through the inner solar system, if the comet were on a bound orbit, which it is not, the nucleus would gradually erode, shrinking with each perihelion until nothing remained but a rubble pile of refractory material, inactive and dark. For 3I Atlas, there will be no multiple passages. This is a single encounter. One opportunity for the sun to warm the ice, one release of gas and dust, and then the comet will recede into darkness, its activity ceasing as it crosses back beyond the snow line. Only dust and light scattered through the void. The grains drift, the photons scatter, the universe expands around them, and the comet continues, shedding fragments of itself into the solar wind, leaving a trail that will persist for weeks or months before dispersing entirely. The concept of perihelion, the point of closest approach to the sun, carries with it a certain inevitability. For 3I Atlas, this moment approaches steadily, predictably, calculable to within seconds based on gravitational equations refined over centuries. The comet follows a hyperbolic trajectory, meaning it is not bound to the sun, not destined to return. It will pass perihelion once, swing around the sun's gravity well, and depart forever into interstellar space, accelerated outward by the same gravitational slingshot that brought it inward. At perihelion, the comet will be approximately 0.4 astronomical units from the sun, closer than Mercury's orbit, within the realm where solar radiation becomes intense, where temperatures rise high enough to sublimate not just water ice, but also more refractory materials. The surface will heat to several hundred Kelvin, perhaps exceeding 400 Kelvin in regions facing the sun directly. At these temperatures, the outgassing rate will peak. The coma will reach its maximum size, and the interaction with the solar wind will be most vigorous. But perihelion is still weeks away. For now, The comet remains in the approach phase, gradually warming, gradually brightening, its activity increasing in a manner that is somewhat predictable but also subject to surprises. Comets are notorious for unexpected behavior, sudden brightening or fading, outbursts where activity spikes briefly before subsiding, fragmentation events where the nucleus splits into pieces. These events reflect the complex internal structure of cometary nuclei, which are not homogeneous ice balls but heterogeneous mixtures of ice, dust, and voids. The nucleus of 3I Atlas, like all cometary nuclei, is thought to be a low-density object, porous and fragile. The term rubble pile is sometimes used, suggesting a loose aggregation of smaller components held together weakly by self-gravity and ice sintering. Mechanical strength is minimal. If the nucleus were brought to Earth and placed on the ground, its own weight would likely cause it to collapse. Unable to support itself under terrestrial gravity, in space, where gravity is negligible, the nucleus maintains its shape, but it is vulnerable to disruption by thermal stresses, tidal forces, or rotational instability. Thermal stresses arise from temperature gradients. As the surface heats during the day, the comet's day, defined by its rotation period, the outer layers expand. At night, they cool and contract. The repeated expansion and contraction can induce cracks, particularly if the material is brittle. Over time, these cracks may propagate into the interior, weakening the structure. Eventually, a section of the surface may detach and drift away, increasing the comet's activity temporarily as fresh ice is exposed. Tidal forces become significant only when the comet passes very close to the Sun or to a planet. For 3I Atlas, perihelion at 0.4 AU is close, but not close enough for tidal disruption. The Sun's gravitational gradient across the nucleus is too weak. However, other comets have been observed to fragment during close solar approaches, torn apart by tidal stress or by the pressure of rapid outgassing. Each fragment then becomes a separate nucleus, outgassing independently, creating multiple comae and tails that gradually diverge as the fragments follow slightly different orbits. Rotational instability is another possibility. If the nucleus is spinning too rapidly, centrifugal forces can exceed the material's tensile strength, causing it to fly apart. Cometary nuclei can spin up due to outgassing torques. Jets of gas escaping preferentially from one side create a reaction force that imparts angular momentum. Over time, the rotation period decreases. If the spin becomes fast enough, the nucleus becomes unstable. This process is thought to have caused the fragmentation of several observed comets, though proving it definitively requires detailed modeling and high-resolution imaging. At 3I Atlas, the rotation period of approximately 8 hours is not particularly fast by cometary standards. Some comets rotate in just a few hours, while others take days. 8 hours is moderate, suggesting that rotational instability is unlikely, at least in the near term. But the situation could change as the comet approaches perihelion and outgassing intensifies. Jets may become more active, torques may increase, and the rotation period may decrease. Monitoring the comet's light curve. The variation in brightness over time provides clues about rotational changes, though interpreting the light curve is complicated by changes in the comet's orientation relative to Earth and the Sun. The internal structure of the nucleus remains largely mysterious. Radar observations of a few comets have provided some information about subsurface layering and density variations, but 3I Atlas is too far away and too small for such observations. What lies beneath the surface, how deep the ice extends, whether there are layers of different composition, whether voids or cavities exist, is unknown. The surface itself is all that can be observed directly, and even then, only at resolutions of kilometers at best. Some models suggest that cometary nuclei are stratified, with an outer mantle of dust that insulates the ice beneath. This mantle forms as sublimating ice leaves behind refractory particles that accumulate on the surface. If the mantle becomes thick enough, it can suppress outgassing entirely, rendering the comet inactive despite the presence of abundant subsurface ice. Other models propose a more heterogeneous structure, with ice-rich and ice-poor regions interspersed, creating a patchy outgassing pattern. Observations of other comets have revealed both types of behavior. Some comets show uniform, diffuse comae, suggesting relatively homogeneous outgassing. Others display discrete jets emanating from specific locations on the nucleus, indicating localized active areas. 3Su au Atlas, based on current observations, appears intermediate. Its coma is somewhat diffuse, but there are hints of asymmetry that may indicate jets, though the evidence is not conclusive. As the comet warms, new regions may become active. Ice that was previously too cold to sublimate may reach the threshold temperature and begin releasing gas. Alternatively, active regions may become inactive if they are covered by dust or if the ice reservoir beneath them is depleted. The evolution is difficult to predict without detailed knowledge of the nucleus's structure and composition. Scientists have constructed thermal models to simulate how heat propagates into the nucleus and where sublimation is likely to occur. These models treat the nucleus as a porous medium and solve equations for heat conduction, vapor diffusion, and sublimation. The models can predict outgassing rates and coma compositions as functions of heliocentric distance, but they require assumptions about porosity, thermal conductivity, ice distribution, and other parameters that are poorly constrained. Different assumptions lead to different predictions, and without in situ measurements, it is difficult to determine which assumptions are correct. One prediction that most models agree on is that the comet's activity will peak near perihelion and then decline as it moves outward. This is observed universally among comets. Activity increases as the comet approaches the Sun and decreases as it recedes. The asymmetry between inbound and outbound activity can vary. Some comets are more active after perihelion than before, possibly because the outbound phase allows previously heated subsurface layers to release their stored gas. Others show symmetric activity curves. For 3I Atlas, the activity curve is still being mapped as observations continue. Only a predictable orbit, and yet the comet surprises. The equations describe the trajectory, but the ice does what it will. The universe offers its calculations, and the comet, unaware of them, continues warming. Magnetic reconnection in the comet's tail, mentioned earlier, deserves deeper consideration. It is a process fundamental to plasma physics, occurring wherever oppositely directed magnetic field lines are pressed together. In the comet's environment, the draped magnetic field creates precisely such a configuration in the tail's current sheet, where field lines from opposite sides of the comet converge. The plasma there is thin. The magnetic field is weak, but the geometry is ideal for reconnection. The process begins with a small perturbation, perhaps a fluctuation in the solar wind, or a wave propagating through the tail. This perturbation brings oppositely directed field lines closer together. In classical magnetohydrodynamics, field lines cannot break or merge. They are frozen into the plasma and move with it. But classical magnetohydrodynamics is an idealization. At small scales, on the order of the ion gyroradius or the electron inertial length, the frozen-in condition breaks down. Kinetic effects become important, and field lines can reconnect. When reconnection occurs, the topology of the magnetic field changes. Field lines that were separate merge, forming new connections. The process releases magnetic energy, converting it into kinetic and thermal energy of the plasma. Particles near the reconnection site are accelerated to high velocities, sometimes reaching energies far exceeding the thermal background. These energetic particles can produce observable signatures, X-ray emission, as mentioned, or bursts of radio waves, or enhancements in the ion tail's brightness. Reconnection also creates jets of plasma that shoot away from the reconnection site in opposite directions along the newly reconnected field lines. These jets carry mass and momentum, contributing to the overall dynamics of the tail. If reconnection is occurring continuously or quasi-continuously, as is thought to be the case in many cometary tails, the cumulative effect is a steady outflow of plasma downstream, helping to maintain the tail's structure and to sweep ions away from the coma. The rate of reconnection, how quickly magnetic energy is converted to particle energy, is a topic of ongoing research in plasma physics. Theoretical models predict reconnection rates that depend on parameters like the plasma resistivity, the magnetic field strength, and the presence of turbulence. Observational measurements at Earth's magnetosphere, at the Sun's corona, and at a few comets have provided data to test these models, but significant uncertainties remain. Reconnection is a multi-scale process, involving physics from the electron scale up to global scales, and no single model captures all the relevant details. At 3I Atlas, reconnection is expected but not yet directly observed. The comet is too distant, the tail too faint, for the kind of high-resolution, high-cadence observations needed to detect individual reconnection events. Instead, the evidence is indirect variability in the tail's brightness, the presence of energetic particles detected by distant spacecraft, the observed perturbations in the solar wind's magnetic field. Each piece of evidence is consistent with reconnection, but none proves it unequivocally. One signature that would provide stronger evidence is a plasmoid, a detached loop of magnetic field containing trapped plasma. Plasmoids are created when reconnection severs a portion of the tail, releasing it as a coherent structure that moves downstream. Optical observations of other comets have captured plasmoids as bright knots that separate from the main tail and drift away. For 3I Atlas, no such features have been seen yet, but the comet's activity is still increasing, and plasmoid production may become more frequent as the interaction intensifies. The solar wind's role in driving reconnection cannot be overstated. Variations in the wind's magnetic field orientation directly affect the reconnection rate. When the interplanetary magnetic field rotates such that its component perpendicular to the tail's current sheet becomes large, reconnection is enhanced. When the perpendicular component is small, reconnection may nearly cease. This sensitivity means that reconnection at comets is episodic, tied to the variable nature of the solar wind. Researchers have attempted to correlate tail disconnection events at other comets with solar wind measurements, seeking to establish causal relationships. The correlations are often strong, but not perfect. Sometimes disconnections occur when expected. Other times, they do not. The discrepancies may reflect gaps in the data, or they may indicate that our understanding of the triggering mechanisms is incomplete. Either way, the comet's tail remains a laboratory for studying reconnection under conditions difficult to replicate on Earth. The energy released by reconnection is not trivial. Although each individual event releases a modest amount of energy, perhaps equivalent to a small terrestrial lightning strike, the cumulative energy over the comet's active lifetime can be substantial. This energy goes into accelerating ions, heating the plasma, and generating waves. Some of it may also go into accelerating electrons to relativistic speeds. creating energetic electron beams that produce radio bursts when they interact with the plasma. Radio observations of comets have occasionally detected such bursts, fleeting signals at frequencies ranging from kilohertz to megahertz. The bursts are thought to be generated by electron beams exciting plasma oscillations, which then convert to electromagnetic radiation. The exact mechanism is analogous to processes observed at Earth's bow shock and in the solar corona. For 3I Atlas, radio observations are planned, but as of now, no bursts have been reported. The comet may simply be too quiet, or the bursts may be occurring at times or frequencies not covered by the observations. Beyond radio, other wavelengths may carry information about reconnection. Infrared observations could detect heated plasma or warm dust near the reconnection site. Ultraviolet observations could reveal emission from highly ionized species created by energetic particles. Each wavelength provides a different perspective, and combining observations across the electromagnetic spectrum offers the most complete picture. But coordinating such multi-wavelength campaigns is challenging, requiring collaboration among many observatories and careful scheduling. The comet, meanwhile, continues its journey, indifferent to the reconnection occurring in its wake. Magnetic field lines merge and separate, plasma jets shoot downstream, energetic particles scatter into the solar wind. The tail glows faintly, a testament to processes occurring at scales too small to see directly, detectable only through their collective effects. And the universe, as always, proceeds without commentary, without acknowledgement, simply unfolding according to the laws that govern charged particles in electromagnetic fields, only plasma and fields, rearranging themselves endlessly. The reconnection continues, the energy dissipates, the tail evolves, and the comet drifts onward, leaving behind a trail of ionized gas that stretches into the dark, fading slowly, becoming indistinguishable from the background after sufficient time and distance. The heliosphere itself, the vast bubble of solar influence within which all these processes unfold, is not infinite. It has boundaries, edges where the solar wind's dominance ends and interstellar space begins. The outermost boundary is the heliopause, located roughly 120 astronomical units from the Sun, where the solar wind's pressure balances the pressure of the interstellar medium. Beyond the heliopause, the Sun's magnetic field no longer shapes the plasma environment. The Voyager spacecraft, launched in the 1970s, crossed this boundary in the 2010s, becoming the first human-made objects to enter interstellar space. Between the heliopause and the inner heliosphere lies the termination shock, where the solar wind transitions from supersonic to subsonic as it encounters the resistance of the interstellar medium. This shock, like the bow shock at a comet, is a place of turbulence and energy conversion. The solar wind slows, heats, and changes character. Beyond the termination shock is the heliosheath, a region of compressed, slowed solar wind that extends to the heliopause. 3II Atlas, currently only a few astronomical units from the Sun, is deep within the heliosphere, far from these outer boundaries. But its origin lies beyond them. The comet formed in interstellar space, or perhaps in another stellar system, and crossed the heliopause on its way inward. During that crossing, it entered a new environment from the cool, dense interstellar medium into the hot, rarefied solar wind. The transition would have been gradual, occurring over months or years as the comet traversed the heliosheath. The interstellar medium, though far more tenuous than any terrestrial atmosphere, is denser than the solar wind at large distances from the Sun. It consists primarily of neutral hydrogen atoms, with smaller contributions from helium and trace amounts of heavier elements. The density is perhaps 0.1 atoms per cubic centimeter compared to the solar wind's 0.011 ions per cubic centimeter at similar distances. This difference in density affects how neutral atoms interact with the heliosphere and, indirectly, with objects like 3A Atlas. Neutral atoms from the interstellar medium can flow into the heliosphere relatively unimpeded by the solar wind's magnetic field, because they carry no electric charge. Some of these atoms become ionized by solar ultraviolet radiation or by charge exchange with solar wind ions, converting them into pickup ions that are then swept outward. This creates a population of interstellar pickup ions throughout the heliosphere, distinguishable from solar wind ions by their different composition and energy distribution. When 3I Atlas was outside the heliopause, it was immersed in the interstellar medium, experiencing a different radiation environment than it does now. Cosmic rays, high-energy particles from supernova remnants and other sources are more abundant in interstellar space than within the heliosphere, because the heliosphere's magnetic field partially shields the inner solar system from them. The comet's surface, exposed to this radiation for millions of years, accumulated chemical changes, alterations in the molecular structure of the ice, and in the organic compounds embedded within. These radiation-induced changes may affect the comet's behavior as it outgazes. Molecules that were altered by cosmic ray bombardment may sublimate at different temperatures or produce different daughter species when photodissociated. Detecting such differences requires comparing 3E Atlas to comets that formed within the solar system and have not experienced the same radiation history. Some differences have been noted. The elevated carbon monoxide, certain unusual spectral features, but attributing them definitively to radiation processing versus compositional differences remains difficult. The comet's journey inward through the heliosphere took thousands of years, assuming a typical interstellar velocity of a few tens of kilometers per second. During this time, the comet's surface gradually warmed, though the warming was initially imperceptible, the temperature rising from perhaps 10 Kelvin in interstellar space to 20 or 30 Kelvin as it crossed the outer heliosphere. Only within the last few years, as it approached the inner solar system, did the warming accelerate noticeably. The trajectory itself is shaped by the sun's gravity and, to a much smaller extent, by radiation pressure and outgassing forces. As the comet outgases, the escaping gas exerts a small reaction force on the nucleus, analogous to a rocket engine. This non-gravitational force can alter the comet's orbit slightly, shifting the perihelion time by hours or days compared to purely gravitational predictions. For 3I Atlas, the non-gravitational forces are small because the comet is relatively inactive, but they are not negligible. Astrometrists tracking the comet's position refine their orbital models continuously, incorporating the latest observations to improve predictions. The comet's hyperbolic orbit means it is not gravitationally bound to the Sun. Its orbital energy is positive, meaning it has more than enough velocity to escape the Sun's gravity well. After perihelion, it will accelerate outward, climbing out of the potential well and eventually resuming a velocity similar to its initial approach velocity, though in a different direction. Within a few years, it will cross back through the termination shock and heliopause, re-entering interstellar space. Within millennia, it will be light years away, drifting through the galaxy, possibly encountering other stellar systems in the distant future. Or perhaps not. The galaxy is vast, and the space between stars is emptier still. The probability that 3I Atlas will encounter another star closely enough to be perturbed significantly is low, though non-zero. More likely, it will wander indefinitely, a frozen relic of one brief moment in one stellar system, preserved by the cold of interstellar space, inactive and dark, until perhaps some distant epoch when it is swept up by a molecular cloud and incorporated into the formation of new stars and planets. Such is the fate of interstellar comets' transient visitors, carrying information between stellar systems, linking the processes of star formation across space and time. Each one that passes through the solar system offers a glimpse of conditions elsewhere in the galaxy, a sample of material formed under different circumstances. The scientific value is immense, but the opportunities are rare. 3I Atlas is only the second confirmed interstellar comet observed in detail, following 2I Borisov in 2019. How many others pass undetected is unknown, though statistical estimates suggest perhaps one per year enters the inner solar system. Detecting these objects requires vigilance, telescopes scanning the sky continuously, alert systems triggering when unusual motion is detected. Even then, many may be missed, those that are faint, or that approach from angles poorly covered by surveys, or that happen to pass when weather or scheduling prevents observations. The ones that are detected receive intense scrutiny, every available telescope pointed at them, data collected across all wavelengths, researchers racing against time before the object recedes into faintness. Only a visitor, and already it departs. The encounter is brief by astronomical standards, measured in months, a negligible fraction of the comet's total existence, and the heliosphere, vast and enduring, absorbs the visit with hardly a ripple, its boundaries unchanging, its structure persistent. The implications of 3I Atlas extend beyond the comet itself. Each observation, each measurement, contributes to a broader understanding of how solar wind interacts with obstacles, how plasma behaves in rarefied environments, how magnetic fields structure themselves around bodies that lack intrinsic magnetization. These are questions relevant not only to comets, but to planets, asteroids, moons, any object exposed to the solar wind's flow. Consider Mars, a planet that once possessed a strong magnetic field but lost it billions of years ago. Without this protective shield, the Martian atmosphere is exposed directly to the solar wind, which strips away atmospheric particles through a process similar to ion pickup at comets. Over geological time, this stripping has removed much of Mars's original atmosphere, transforming the planet from a potentially habitable world with liquid water on its surface to the cold, dry desert observed today. Understanding the details of solar wind interaction, the bow shock formation, the ion escape rates, the role of magnetic draping helps refine models of atmospheric loss, which in turn inform estimates of Mars's past climate and habitability. Venus, though it lacks an intrinsic magnetic field like Mars, retains a thick atmosphere because the planet is more massive and its gravity holds atmospheric particles more tightly. Still, the solar wind interacts with Venus's ionosphere, creating a bow shock and an induced magnetosphere shaped by the draped solar wind magnetic field. Spacecraft orbiting Venus have mapped this interaction in detail, finding similarities to cometary interactions, but also differences due to the planet's size, gravity, and atmospheric composition. Each new observation of a comet provides comparative data, revealing which aspects of the interaction are universal and which depend on specific conditions. Even Earth, with its strong intrinsic magnetic field, is not immune. The solar wind compresses Earth's magnetosphere on the day side and stretches it into a long tail on the night side. Reconnection in this tail accelerates particles that precipitate into the atmosphere near the poles, creating auroras. During geomagnetic storms caused by coronal mass ejections impacting Earth's magnetosphere, the interaction intensifies, and auroras can be seen at lower latitudes. The same physics that governs reconnection at comets governs reconnection in Earth's magnetotail, making comet observations relevant to understanding space weather and its effects on satellites and power grids. Beyond the solar system, the principles apply to exoplanets orbiting other stars. Many exoplanets are close to their host stars. Within distances where stellar winds are intense, these planets likely experience interactions far more extreme than anything in the solar system. Their atmospheres may be stripped away rapidly unless protected by strong magnetic fields. Estimating exoplanet habitability requires modeling these interactions, and observations of comets provide ground truth for the models. The physics is scalable. What occurs at a comet in our solar system informs predictions about planets orbiting distant stars. There is also the matter of organic chemistry. Comets deliver organic molecules to planetary surfaces, contributing to the inventory of prebiotic compounds available for the origin of life. When a comet like 3I Atlas passes through the solar system, some of its dust grains will eventually be captured by planets or settle onto moons. Earth itself has accreted cometary material throughout its history, particularly during the late heavy bombardment roughly 4 billion years ago, when the impact rate was much higher than today. Whether this material contributed to the origin of life remains speculative, but the possibility cannot be dismissed. The dust from 3I Atlas, though unlikely to reach Earth in significant quantities, adds to the interplanetary dust complex a diffuse cloud of small particles that fills the solar system. These particles scatter sunlight, creating the zodiacal light visible from dark locations as a faint glow along the ecliptic plane. They also spiral slowly inward due to the Poynting-Robertson effect, where radiation pressure and the particles' orbital motion cause them to lose angular momentum and drift toward the sun. Eventually, they either vaporize in the sun's heat or are swept up by planets. Interstellar dust, which 3I Atlas may carry, is of particular interest. Such dust grains formed in other stellar environments, around other stars with different metallicities and nucleosynthetic histories. Analyzing their compositions provides information about the galactic chemical evolution, about how elements are synthesized in stars and distributed through space. Pre-solar grains found in meteorites have revolutionized our understanding of stellar processes. Grains from interstellar comets could do the same, if they can be collected and studied. Sample return missions to comets have been proposed. Though none have yet succeeded in returning material from an interstellar visitor, the European Space Agency's Rosetta mission orbited Comet 67P Churyumov-Gerasimenko and deployed a lander, but the comet was a solar system native. NASA's Stardust mission captured dust from Comet Wild 2 and returned it to Earth, providing the first samples of cometary material for laboratory analysis. Those samples revealed complex organic molecules, including amino acids. Confirming that comets contain the building blocks of life, a mission to 3I Atlas would be scientifically invaluable but logistically challenging. The comet was identified too late for a spacecraft to intercept it with current propulsion technology. Future missions might use advanced propulsion ion drives, solar sails to reach interstellar visitors more quickly, or they might be pre-positioned in the outer solar system, waiting for targets of opportunity. Alternatively, missions could target interstellar objects that are discovered earlier, when they are still far from the sun and moving more slowly. For now, remote observations must suffice. Telescopes on Earth, spacecraft in heliocentric orbits, monitoring stations across the solar system all contribute pieces of the puzzle. The data are archived, available for analysis and reanalysis as new techniques are developed and new questions are asked. This is how science often works. Observations outlive the initial analyses, becoming resources for future generations of researchers who approach the data with fresh perspectives. The comet itself, unaware of these broader implications, continues its outgassing. It does not know it is being studied, does not know it carries information valuable to understanding planetary atmospheres, space weather, organic chemistry, stellar evolution. It simply warms, sublimates, and drifts through space, governed entirely by physical law, indifferent to significance. Only a comet, and yet it touches so many questions. The solar wind bends around it. The magnetic field drapes over it. Particles are accelerated, waves are generated, and scientists, scattered across a planet 150 million kilometers away, point instruments skyward, collecting photons, recording data, constructing understanding from light. As perihelion approaches now only days away, the comet's activity reaches a crescendo. The outgassing rate has increased tenfold from the levels observed weeks ago. The coma now spans more than 1 million kilometers, though still invisible to the naked eye from Earth. The ion tail has grown to several million kilometers in length, a faint blue streak detectable in long exposure images from dark sky locations. The dust tail, broader and more diffuse, curves gently along the comet's orbital path, reflecting sunlight with a slightly yellowish hue. Observations intensify. Telescopes track the comet continuously, limited only by daylight and weather. Spectrographs dissect the light, revealing emission lines from dozens of molecular species: water, carbon monoxide, carbon dioxide, hydrogen cyanide, methanol, formaldehyde, and others. The relative abundances shift as different ice reservoirs become active, as temperature gradients evolve within the nucleus, as solar radiation varies in intensity. Each measurement adds to the data set, each spectrum a snapshot of the comet's state at a particular moment. The solar wind monitoring stations report fluctuations consistent with an enhanced interaction. Magnetic field measurements show increased variability, with amplitudes higher than baseline by 20 to 30%. Plasma density exhibits spikes and dips, occurring quasi-periodically with timescales that may relate to the comet's rotation. Energetic particle detectors register bursts of ions with energies exceeding those typical of the ambient solar wind, possibly accelerated at the bow shock or in reconnection events. Yet, despite the increased activity, the comet remains modest by historical standards. It is not a great comet, not an object that will be remembered for generations. It will not outshine Venus.